to match with the book.
Yeah, there we go.
I'm gonna get y squared and then x squared plus x. Yeah.
Go ahead, that's one more.
Yeah, but that's not what the book.
I didn't see it on the computer.
Yeah, the book didn't have that.
That's what you know.
And I just put it on Wolfram also and copied the thing over.
Right.
Happy free chocolate, cheap chocolate day.
Can you see that?
Yeah, chocolate.
Not yet. You probably won't because I've been nice all day.
Chocolate what?
Today is cheap chocolate day.
Is it? Oh.
Yeah.
Right. Oh man, Valentine's Day was yesterday.
Yeah.
It was Taco Tuesday.
Oh god. I know.
What?
I'm sorry.
Taco Tuesday.
I miss Taco Tuesday.
I'm so sorry.
I miss Taco Tuesday.
Oh, but these just came out.
We came on it.
Yeah. So you'll be returning the Staples?
No.
Oh, okay. So you're not borrowing it.
Wow.
I-
You really are going there? Jeez.
Okay, so let's go over homework problem 41. Okay. It's a nice problem in the sense that it puts a lot of things together, especially this domain of definition business that we went over several weeks ago. Okay, so we have the differential equation dy dx equals 2x plus 1 divided by 2y. Okay? And there's an initial condition given that should go from the point -2, -1. Let's just start off integrating. It's variable separable, right? So we get 2y dy equals 2x plus 1 dx. Simply integrating y squared equals x squared plus x plus c, with c is an arbitrary constant. Okay, at this point we'll insert the initial data, namely when y is equal to -2, x is equal to -1. And when you plug that into over here, you find the numeric value of c is equal to -1. So of course, then you get back to here, y squared is x squared plus x -1. So we'll go through this several examples. Which branch of the square root do you take, plus or minus? Okay. Well, what happens is that it's only the negative square root that'll get you through -2, -1. Okay, so that's why it's the minus square root over there.
What happened to the 1/2? The
1/2? Where's the
when you
1/2?
integrate y squared, or when you integrate y?
Integrate 2y, you get y squared.
Oh, it's 2y.
Yeah, 2y, sorry. Okay, so the next part asks you to kind of graph this, okay? And you know already, basically, you have a radical under there. There could be points where it's negative and it's going to be imaginary. You only want to get a real solution. What's nice about MATLAB, and matter of fact, other computer programs, is that if you plot something and it comes out to be imaginary, it just leaves them off the plot. So you don't have to even like worry at this point about, gee, what range of x should I take? I don't know, I think maybe when x goes to x equals -3 to 3 or something like that, okay? And of course, MATLAB did computation to get imaginary values, but when it plotted it, it just left them out. Notice there's nothing over here between 0 and approximately 0.6 and 0 and -1.6. These are approximate numbers I got from the graph, just looking at them. We're going to go back and get the exact values of those coordinates, okay? Basically, here's what we have, and here's basically what the graph looks like, and clearly we want to be on this branch over here. Okay, now we got to get a little more precise, and the problem asks for what's the domain of definition for this solution, okay? And remember, that means that the function y that I write over here has to satisfy the differential equation and the initial condition, and has to have a real value. And we see that probably goes from -infinity to approximately -1.6. So let's get that number precisely, okay? And that's easy enough. We can just look at this quadratic, okay, and graph it, okay, and find out where the roots are, okay? So what I have over here now is a graph of the function of x squared plus x minus 1. It's basically a parabola, and it goes something like this. Okay, so this is x, and over here I plotted x squared plus x minus 1. Okay? That's what's under the radical over there. Okay. You see when x is equal to 0, it has a value of -1. Okay, so this is 0, -1. Okay? The vertex is someplace over there. And it crosses the x-axis at 2 points, x1 and x2. These are the 2 points, right? And you can see basically over there it becomes negative, and that's what's happening over here, okay? So, everyone knows how to solve a quadratic. I won't do that. You'll find out that the two roots are x1 equals -1/2, parentheses, 1 plus radical 5. Okay, and that's approximately equal to -1.6 d2. So that's one that the graph got, right? -1.6, and that's to the left over there. And the other root, x2, if you get it exactly, it's 1/2 parentheses 1 plus radical 5. No. Half. This all comes from the quadratic formula, right? You should be able to get this. And that's about 0.62. Okay, and that's basically this guy, and that's what I saw, when I plotted it. Okay? So clearly for this graph over here, for the second part, the domain of definition goes from here all the way up to here, right? So the domain, basically, the domain of the solution of initial value problem is all values of x minus infinity less than x less than x1. Okay, where x1 is that number over there, -1.62 approximately, or exactly -1/2, 1 plus radical 5. Okay? Now what happens is that one of the questions is, do I basically make this less than x1 or less than or equal to x1? Okay? It looks like the graph does go through, that point x1, so that would say I should make it less than or equal to, but you'll notice that the slope at that point becomes infinity, right? I can't divide by 0, so it's this, not less than or equal to. Okay? So when you check your domain of definition, you have to be careful. Again, things like the radical being positive, but of course, radical can be 0, but in this case, when the radical goes to 0, you have an infinite slope. So you have to rule out that point. So that would be the domain of definition for this problem. Any questions? Yeah, it's pretty straightforward. Like I say, what's nice is that you can get at least an estimate by just graphing this thing blindly. And like I said, MATLAB ignores the imaginary parts. Okay. Okay, today we get to do, in fact, I think something very interesting. This is going to be the first equation that we'll be able to integrate, okay, first order linear, and it's something which, unless you took the course before or you read ahead in the book, you probably didn't know how to do. Okay, so this is a whole thing we talk about first order linear equations. Obviously linear differential equations, right? First order linear. Okay, remember I said most of the course will be linear equations because nonlinear are very hard to do. And why not start with the simplest one? Let's go first order linear equation. If you go back, a few weeks when we talked about equations and all the classifications, we wrote down the most general linear equation of first order. Actually, we did it for nth order. And basically the form of that was a1 of x dy dx, right? Plus a0 of x times y is some function which is called g of x. Right? That's the most general first order linear equation. It's first order because it only contains the first derivative of y with respect to x. And it's linear because it only contains linear combinations of y and its derivative. But the functions a1 of x, a0 of x, and g of x can be anything. Okay? X cubed sine x, anything. Okay? And what's going to be amazing is I'm going to show you that this equation, in principle, can always be integrated. You always can solve it, which is pretty interesting, given the fact it has variable coefficients. Okay? So, what's the idea? Okay? The first thing which I'm going to do is put this in what's called a standard form, right? It's obvious that you always can divide through by a1 of x. So the equation that we're going to study basically is dy dx. Let's just call this function p of x times y is equal to f of x. Clearly f of x is just g of x over a1, and p of x is just equal to a1 over, p of x is a0 over a1, and g over a1 is f of x. Okay, now you have to be very careful. All the formulas I'm going to derive, for all the formulas, it's going to be 1 for the solution, how to get that. Always assume that the coefficient of dy dx is equal to 1. This is where most students make mistakes. Okay, when you have a problem that's first order linear and you use this technique, immediately divide through by this coefficient, so it starts off with 1 dy dx. You always can do that. Okay, so therefore there's no less in generality in studying this equation, because any first order linear can always convert it to that form. Okay, what I'm going to do now is multiply this equation through by a function unknown at this time called phi of x. This is going to be called the integrating factor, and you'll see in a second why I'm doing this. Phi of x dy dx plus phi of x p of xy equals, obviously on the right, phi of x f of x. Now that seems kind of ridiculous. You know, why am I multiplying through by a function phi of x? I must tell you that the way I'm doing it is different than the book. I think it's much shorter and much easier to understand. So you may want to just, take some notes on this. What the idea over here is to look at the left-hand side, and at this point, phi of x could be anything. So I want to choose phi of x so that this equation assumes a very nice form. And basically, here's what's going to happen. Choose phi of x such that the left-hand side, which is this thing over here, phi dy dx plus phi of x py, is equal to the derivative with respect to x of phi of x times y. If we can find a phi of x that does that, let me just show you why is it so simple. Because let's assume, and we'll show that we can, that we find a function phi of x, a magical function, it's called the integrating factor. So this left-hand side collapses down to d by dx of the product of the integrating factor with y. Then the equation would read what? It would become d by dx of phi y equals the right-hand side. You could integrate this, that's easy, because it's already a derivative, right? So it would be phi times y. Then you'd have the integral of phi times f. Okay, you do that. Divide through by phi and you have y. Okay? So the big thing is, can we find a function phi of x that does this? Okay? Well, the way I'm going to show you how to get it is I'm going to expand this desired form, compare with this, and that will dictate how we have to choose phi of x. Okay? So now, if the left-hand side is equal to this, what do we have on the left now? So now we have phi of x dy dx, right? Which of course I do have, right? And then remember, it's the product rule, right? Plus d phi dx times y. Okay, right? That's what the left-hand side is now. Just using the product rule. But what's the left-hand side that I have over here? Well, if I basically use this guy now, well, that's supposed to be identical to phi of x dy dx, right? Plus phi p. Phi of x, p of x times y. Everybody see what I did over here? Right? Here's a desired form. Okay, well, then when I expand it, I'm going to get phi y prime plus phi prime y. But I've got on the left-hand side phi dy dx plus phi of x p of x times y. The phi of x dy dx cancels, right? And now I'm left with the following. Look at the coefficient of y. The phi dx times y, what do I have over here? Phi p y. Therefore, this says that I have to choose phi of x in such a way that the phi dx, that's the y coefficient, is equal to, what's my y coefficient over here? Phi of x, p of x. Now remember, f of x is given, p of x is given. The only unknown here is phi, and that's my integrating factor. Well, that's variable separable, right? So this becomes the differential of phi divided by phi, okay, equals P of x dx. Everybody can integrate 1 over phi d phi, right? That's just the natural logarithm of phi. And over here, I don't need the most general solution with the arbitrary constant because I want to choose the simplest phi of x that I can find, right? Any phi of x, basically, that will work over here in the sense of being an integrating factor is fine. So this is the simplest thing. We can have basically log of phi is the integral of P of x dx. Again, in practice, when we do a problem, P of x will be given. We know that. And we can do the integration, hopefully, and get just the right-hand side purely as a function of x. So therefore, the integrating factor, P of x, is equal to the exponential of the integral of P of x dx. Okay? So let's kind of just put this kind of as an algorithm, and then we'll just do some problems with it. Okay? The other thing you kind of like to commit to memory over here is, remember, you put it in this form, okay? And to get the integrating factor, you integrate this and then take the exponential. Then you'll see when we multiply through, the left-hand side will be known already. It's d by dx of the integrating factor times y. Okay. So, let's just kind of summarize this. To solve any first order linear, right, ODE, ordinary differential equation. So the first step is put in standard form i.e. it should be of the form dy dx plus some function, it's called P of x times y, equals a function of x. And you always can do that, right? Second step, find integrating factor. That's this function phi we were talking about.